This lesson begins our unit on systems, and we will be graphing systems today. So because we're graphing systems, you'll see that this builds upon a lot of the linear equation work we've been doing so far this year. So let's first start by defining what a system is, and it is two or more lines on a coordinate plane. So if you have two lines in your grid, then that is, by definition, an example of a system. We will find that some systems, some lines, if we have two or more in the plane, will intersect each other. And so the special relationship that multiple lines in a grid have about that intersection can be pulled from that system. So those points of intersection will be what we call the solution to those systems. So when our lines do in fact intersect, this intersection is known as the solution to the system. So for example, here we have two lines in a grid, and here's actually the same graph. Two lines in a grid, and we have the two lines intersecting at this point 1, 1. So for this system, which is just made up of these two lines, I could call this line 1 and line 2. The solution itself is the point 1, 1. So a solution is that one point of intersection. So if you were told to solve a system, what you're looking for is that ordered pair, that point, that x comma y, that is where your two lines intersect. So let's look at this example. This is a system. We have two or more lines in a plane. Here's line 1 and line 2. However, would this type of system have a solution? And so what you're seeing are two parallel lines, and because they're parallel, we know by definition that that means they will never intersect. They have the same slopes, but they'll never intersect, different y-intercepts. So if the solution to a system is the point where your lines intersect, but these never intersect, then this is a case where we will find that our system has no solution. So there are times when you are solving a system where you won't actually be able to find a solution for that system, and that is when your lines are parallel. So if lines are parallel, there will be no solution because they never intersect, and solutions represent the point of intersection. All right, so here's a second scenario to consider. This time we actually have, and it's hard to show, but we have this line, and this is actually line 1, and then right on top of it, which my board's not perfectly aligned, but I'm doing my best to show it, lies line 2. So really what this is trying to show is that we have the exact same line or same equation, two lines that are the same on top of each other. And so what we're wondering here is there a solution here? Is there a point of intersection? Well, if the two lines are on top of each other, then that means they share many points in common. And we could probably find points all day that they both share, and we definitely could, out to infinity. There are infinite shared points that those two same lines will have. So this is an example of infinite solutions. So we'll often just draw the infinite symbol or write the word infinite with solutions after it. So if the two lines happen to be identical, then there will be infinite answers or solutions because all points on the line will intersect. So if the solution to a system is the point where it intersects, and this one has infinite intersection points, then we have infinite solutions. Okay, so today we're going to explore how to estimate a solution, and we're going to be really using estimation today with the graphing method because we'll find other more exact methods later on this unit. But today we're just going to use graphing to really get a visual of what's going on in our system and make an estimate of that solution. So to estimate our solution, we can graph the two lines and find their intersection. So let's start with these two lines, and I'm going to color code mine, but it might help to just label them. So I'm calling this one line 1. I'll do it in green, and this is my line 2, and I'll do that one in blue. So we're going to start by graphing these. Both of these are in slope-intercept form, which is really helpful for graphing because we can start by plotting. Oops, I didn't mean to cross that out. We can start by plotting the y-intercept first. So if this one has a y-intercept of 3 and then a slope of 1/2, then we start at the y-intercept of 3, then up 1 over 2, up 1 over 2. And so I'm just getting several points on this line in both directions. And once I get that, I'm going to connect those, extend them with arrows on the end. So this is my line 1 graph. Now, if this system has a solution, then it has a point or multiple points for the lines intersect. So let's plot that second line. Its y-intercept is 1 with a slope of -1/2. So down 1 over 2. And I'll go in the other direction, up 1, left 2. Okay, and we'll connect. Hopefully, as you're plotting this, you noticed that this point right here plotted on top of the first line's point. So that point right there is our point of intersection, meaning that that is our solution to the system. So finally, to write the solution, we count out that this is left 2, up 2, meaning the solution is the point -2, 2. And this point is the solution to this system. So this one was a nice clean intersection right on those grid markings. So this is an exact solution. But you can imagine that if the intersection were between grid lines, we wouldn't be able to be so accurate with our writing of the solution. All right, so let's try another one. Here we have y equals 2x plus 1 as line 1. So its y-intercept is 1, up 2 over 1. And I generally like to go in both directions to get plenty of points and connect and label. I'll do the same for line 2. This one's y-intercept is -1 and up 2 over 1. Oops, that's not the right point, sorry. Okay, and going in the other direction. So these two lines, I hope you can tell by the way they're written, have the same slopes, which means that they are parallel. So if these lines are parallel, they never will actually intersect, meaning that there is no solution. We still want to graph it to visually show that they won't intersect, but you would probably be able to tell right from their slopes that they wouldn't have any intersection, so no solution. All right, try this one on your own. Go ahead and estimate the solution by graphing both equations. And in just a moment, or when you're done, click pause to practice and then play when you're ready to check. Okay, so let's check how you graph this. I have my line 1 or my top equation in blue and the other one in green. And you should have found their solution, the point where they intersect, to be the point -1, 0. Make sure you're writing those in parentheses with a comma in between. Okay, here's another one for you to practice. Go ahead, graph both lines, estimate where they intersect, and then we will check together when you're ready to hit play. Okay, so you have graphed both lines. And this one's a little bit tricky because the intersection is right in here and it's not a clean grid intersection. So if we were to estimate this, I might say it's at, and I don't know, I'm making this up, but -1.75 maybe, and then maybe just below that x-axis to negative, I don't know, I'll say 0.2, just something really small. Okay, so this would be an estimation, and this is again why the graphing method isn't always the most exact method. We will learn ways to calculate this more precisely and get the exact intersection point, like I said earlier. However, for something like this, we're going to just write down an estimation. But we are going to use our calculators, so we'll estimate it by hand first, and then if we notice it's not a clean grid line intersection, we're going to actually use our calculators to help us. So to use our calculators, what we'll do is we will go into a graph, and it can be a graph scratch pad or a graph in a document. You don't have to save these. And we will graph both equations. Once you've graphed them, you're going to hit Menu, Analyze, Intersection in that order. Those are the buttons you'll hit. And then you will select a lower bound and an upper bound, and that will approximate the answer for you. So let's go through that process together. So if you have your calculator, we are going to start by graphing both equations. So I'm just going to my graphing scratch pad, and I'm going to type in the first equation, which was 3x plus 1, I believe. Oh, sorry, plus 5. Sorry, plus 5. And I'm going to hit enter and graph that one. Now hit tab to graph your second equation, which is 2/3 x. So control, division, and 2, down arrow, thirds, x. This one's plus 1, and graph that one. So I've got both lines graphed, and it should match what you graphed by hand. And what we want to do is find where is that exact intersection. So now here's where we'll type Menu, Analyze, Intersection. What this is going to do is find the intersection of our two lines. Now this dashed line comes up, so you'll use your scroll to scroll once to the left, which is the lower bound, and then click, then scroll once to the right and click again, and that's your upper bound. And right there you can see that it brings up a point for us, negative 1.71 comma negative 0.143. Now what's important for you to know is this is way closer, but this is still not exact either, because your calculator is needing to round that decimal at some place. So it looks like it's rounded that second value, the y, to the thousand, and the first decimal to the hundred. So just be aware of that this is definitely much more accurate, but not exactly perfect. So we then can see that we're approximating this answer to be negative 1.71 comma negative 0.143, and you can just copy that down onto your paper. That's the solution you can use. Okay, so once you get that solution, while you estimated it by hand, make sure it is matching your by hand estimation, and then go to the calculator to get a more precise or closer estimation. Okay, let's go ahead and graph this one together, just because they're not both given in slope-intercept form. So the first one we can certainly graph the way it's given. It's y equals 3x plus 6. So the y-intercept is 6, and then we're counting up 3 over 1, or down 3, left 1. Getting several points, 1, 2, 3. Okay, so that's my line 1. Now for line 2, we need it in a form that we can graph from, and it is not in standard form yet. So that means we need to isolate y. So I'm going to add 6x to both sides, giving me 2y equal to 6x plus 12. Then divide through by 2. And right at this point, I hope you notice something, and that is that that equation happens to be the exact same equation as line 1's equation. So this, in fact, and this board, sorry, is not aligned, but anyways, they are the same line on top of each other. So that means there are infinite solutions to this system. Those lines are intersecting infinitely many times. They share infinite common points. So you would write infinite solutions as your estimation here. Okay, from here on out, if you're in class, we are doing some IXL practice that I have posted and linked on our Chapter 5 Systems page. If you're not in class, then you can do this on your own. But I hope that was a good lesson, just kind of introducing systems and how we will estimate their solutions by graphing.